gotta do what you gotta do. Yeah. I appreciate you showing up for whatever. You'll appreciate it too. Welcome back to class. Hopefully everyone's having a decent week. Today we have a lot of non-lecture things to get through, so I'm just going to kind of jump into stuff here. And first, I just want to ask questions. Everything making sense so far? Anything tripping you up, stuff like that? Okay. Again, I know for many of you a lot of this stuff is review and so forth. We will start getting to newer stuff, especially towards the end of this chapter. But as I said before, we got to lay the groundwork, so I just want to make sure we're all on the same page there. I don't expect it to be review for everyone by any means. So if it's not review for you, that would be the norm, I expect. So there you go. Okay, next thing on my list. I made a list so I don't forget. The exam. So a week from today will be the first exam in the course. The exam is made about 50% multiple choice questions, 50% fill-in questions. The fill-in questions will be things such as the math. So the math we've done so far in this course are unit conversions, density, and the metric system. Okay. Remember, for the metric system, there are 3 conversions that I wanted you to know. The kilo, milli, and centi being the 3. So hopefully you got all that taken care of and you're caught up in everything, because we're going to continue going forward, obviously. So math, short answer, and those short answers can be anything from like fill in the blank to what I call a longer short answer. I never ever ask you to write out like an essay, because I don't want to read them. So just about the longest you guys would ever write out is like a paragraph explaining something. That's the longest I would look for. If you want to write more, then by all means, please feel free to do so, but I would never expect it. I've got 40 people in this class, 40 people in my other class, and well, 35 in my third class. So you can imagine that if everyone wrote 2 pages, that would be a lot to read, and so forth, and I don't want to do it. So, and I don't think you guys want to do it either. So there you go. So the fill-ins could be definition. I mean, they could really just be everything that we've done up to this point. The multiple choice, I will base the multiple choice questions off of the ones that make up the homeworks. So if you've gone through and done the homeworks and things like that, you're going to be in much better shape. in terms of the actual exam. So I may change the element. So it may say, what's the atomic symbol for aluminum in the homework questions, and in the exam it'll be like, what's the atomic symbol for silicon? Okay, just change the element, something like that. But the general idea, they'll be the same types of questions as you go through. Does that make sense? All right. Lengthwise, I write it so that it takes about an hour so that you have extra time above and beyond what I think would be an hour. Not how long it would take me. It wouldn't take me an hour to do it, obviously. But from past experience is what an hour is. Generally, I guess, on the shorter side than the longer side. But I want to make enough questions in it so if for some reason you make a silly mistake or something, it doesn't hurt your overall grade all that much. You know, if, for example, there were only 5 questions on the exam and you just silly and mess up one, that's 20% of your grade. We don't want that by any means. But I would guess probably somewhere around 40 questions? Nah, probably not that many. 30 to 40, somewhere in that range. It kind of depends on the makeup of the questions too, to some extent. Math ones I always figure a little more time for as you're going through and figuring them out. But we'll see how it turns out. I haven't written it yet, so I have no idea. When you are done with the exam, you are free to leave. We don't collect the exam, start lecture or anything like that. Just come in, take the exam, done, then go about your day, enjoy your weekend, all of that. The other thing I will mention is remember for the exam, you are not allowed to have programmable calculators or cell phones to do it. And since we're going to be doing math conversions and so forth, I would expect everyone in here to need a calculator for the exam. I know I would need a calculator for the exam. So bring one with you. If, heaven forbid, you forget one, I have 10, 12 of them I can loan out, but that's on a first come, first served basis. So if you're the 13th person, I only have 12, then you have to wait until someone finishes before you get it. So you can do the other questions and then I'll get you one as I can, but that being said, it's just much, much better and easier for you to go to Walmart or whatever and buy a non-programmable calculator. That way you can also practice with it. Remember we talked about how to enter in scientific notation and things like that. So, you know, something you're going to be responsible for knowing for the exam. Okay. I think that's it. You guys have oh, I got one other thing. On Blackboard, as I said before, we're using a new text for this course, so I don't have old versions of exams that go with this textbook. So I wanted to ask you guys, would you like me to put up exams from the old book? Now the old book was structured the same way and so forth. It had different questions and things like that, but it would give you an idea of the level and the types of questions and so forth that I would like. Was that okay if I put that up? I don't want to confuse you by, you know, I really think they'd be directly interchangeable. But that being said, okay. So what I'll do is I'll put up the folder of old exams. They're not going to be like exam 1 from the old one is not going to be exactly the same as exam 1 now by any means. They're not even in the same book because I just kind of go until I stop. But on Blackboard, you can look for that folder starting today. Then I'll put that up for you. You'll have those for the whole term. Okay. Good? Questions? You don't have to bring, well, any paper with you. Like I've had students try and bring periodic tables in with them. I will provide that for you. So don't plan on being able to use a periodic table or something like that. The one I do give you for the exam is just like what's on the walls here, except for the fact that I'll have the English name of the elements there for you as well. So you don't have to memorize the symbols or anything like that. I think that's about it. We got one more class. If I think of things, I'll tell you next class. Right? Okay, so that'll be next Thursday. To see where we are in terms of that, we are going to take our first short quiz today. So let's put away our notes and stuff. So let's take 5 minutes or so. Again, because it's a quiz, you can use your cell phones as a calculator, but I'm asking you just be honest and don't use it to look up answers and so forth. I know not everyone has a calculator with them today when they're pop quizzes. Two minutes left. last 30 seconds. Make sure that your name is on it. Okay, so pass them to the ends of the rows, and I will come pick them up. It doesn't really matter which end. Whatever's easiest. Okay, so I would consider those medium level fill-in questions for you on the exam, except for the extra credit one. The extra credit one's really hard, by the way. So you kind of know where you stand in terms of preparation for the exam and so forth. But with the weekend coming up, I want to run through the questions really quick. So first off, I guess I should ask, any general questions before I get started running through? Okay, so first off, how many milligrams are in 10 grams? Well, to do this, you need to remember the milli conversion, and that is 1,000 milligrams is equal to 1 gram. You got that right? No? Oh, I'm sorry. What did you put? If I could ask. 100? Does anyone know, what's the prefix for 100? Centi.
So what's kilo?
Kilo is 1,000 the other way. So 1,000 grams is equal to 1 kilogram. Okay. This is why this is why I actually like giving the quiz at this point, so that you can kind of catch yourself with these not so important things before going into the exam with time to review. Okay, so here we are then, 10 grams equal to milligrams. So 1 gram is going to go on the bottom. 1,000 milligrams goes on top. Grams cancel, leaving us with milligrams, which is good. So the answer is going to be 10,000. 10,000 milligrams. Second one, how many kilograms are in 500 milligrams? Well, here, I don't know the relationship between the two, so I'm going to use 2 steps, and the first one is going to be milligrams to grams, and then going to kilograms. So we already have the milligrams one. Well, actually, we already got the kilograms one too there. So we can start with 500 milligrams. We want to go to grams. So for every 1,000 milligrams, it's 1 gram. So our conversion is flip-flopped here because we're starting with a different unit. So it's going to be 0.5 grams. Then we need to go to kilograms. And here, we're going to say that for every 1,000 grams is 1 kilogram. So now doing this, I didn't leave myself enough room. 0.0005 kilograms. So these are meant more as unit analysis type problems, setting them up, and then also checking the knowledge of the metric system. Other questions about the, yeah?
How much was that quiz worth?
Well, so it's going to be graded on a scale of 10. At the end of the semester, all the quizzes together are going to be the same as one of the exams. Okay, so we'll have several quizzes through the course, one of which is going to be dropped as well. But that being said, if you don't feel that you did as well as you like, which I'm guessing from your look there, it's a good reminder to keep up on the material as we're going through, because we're not going to take whole days. This is not just for you, for everyone though. We're not going to take whole days to just review for the exam. We'll take a little bit of time and so forth, but you got to constantly keep up with stuff, because more information is going to be thrown at you all the time in the course as we go through. Okay? In the end, technically, it could count as 0 because it could be the one that's thrown out. Even if that's not the case, it's not a huge amount of your score or anything like that. Yeah. Okay. Other questions? Next one. The density of lead. So the density is equal to 11.3 grams per centimeters cubed. What mass of lead is required to make a fishing sinker with a volume of 1 centimeters cubed? So density is equal to mass over volume, and we want to find the mass. So this is going to be volume times density. So plugging it in here, the volume is 1 centimeters cubed. The density is 11.3 grams per centimeters cubed. Those cancel out, leaving us with grams. And then I guess I can do that in my head. 1 times 11.3 is going to be 11.3. So here's a math question having to do with the density. It involves rearranging it algebraically and then plugging in the values, which is almost exactly what you're going to see on the exam. That's really the only type of questions I ever ask on density. Well, the math of density. Questions about that? Okay, now the last one, the extra credit one. The reason why this is extra credit is because we haven't done one like it yet, even though you do have the information for it. So let me write it down real quick. Oh, actually, here, let's do this.
Smarter than the wrong person.
Let's see which one. Okay, so the question is, it takes 12 grams of carbon to make 16 grams of CH4. How many grams of hydrogen are needed to make 48 grams of CH4? Now this is a mathematical question having to do with the laws that we learned last time. So the laws were the law of definite proportions, the law of multiple proportions, and the law of conservation of mass. And this question really has to do with 2 of those 3 laws. So I'll walk you through how to do it, and then we'll try another one on our own. So to start with, it takes 12 grams of carbon to make 16 grams of CH4. So carbon is C, and then we have H as well. So if I start with 12 grams of C, and I end up with 16 grams total, how many grams of the other stuff do I need? 4. Okay. So it takes 12 grams of carbon plus 4 grams of hydrogen to form 16 grams of CH4. Which of the three laws is that? Right? Yeah.
Conservation of energy.
Mass, though.
No.
Conservation of mass. Conservation of mass. Okay? So that's the first one here. So then the question asks, how many grams of hydrogen are needed to make 48 grams of CH4? So going through our steps of unit analysis, with that part, how many grams of hydrogen are needed to make 48 grams of CH4? What is it asking us to find?
Grams of.
Grams of hydrogen. Grams of hydrogen. So the first thing it wants us to find is grams of hydrogen. And what is it giving to us to start with? Right? What's the number associated with it? 48. Okay, so 48 grams of CH4. So that's the first two steps. The third step is, do we know a relationship between grams hydrogen and grams CH4? We do. Okay, looking up at the top here, we know that for every 4 grams of hydrogen, that's going to be 16 grams of CH4. So 4 grams of hydrogen is then going to be 16 grams of CH4. Do you see where that's coming from? Okay, written out this way. Okay. Okay, we'll do another one in a minute. Okay. So, with 1, 2, and 3 answered, we can set up our problem. What does it give us to start with? It's going to be 48 grams of CH4. We want to find grams of hydrogen. So we need a relationship between the two, which is here. CH4 goes on the bottom because that's what's there. So 16 grams of CH4. 4 grams of H goes on the top. Grams CH4 gets canceled out. Grams hydrogen match. And then doing the math, 48 times 4 divided by 16 should be 12. I'll double check that. I have to grab the one that's dead. It's right? Yeah. Okay. I'm getting all nervous up here. So that's 12. So you see how we've got what the problem gives us to start with, what it's asking us to find, and then the relationship between. Now this is the first example where the relationship between is not directly given to you in the problem. You have to derive it from some chemistry knowledge. Okay? And it's going to be a reoccurring thing as we go through. Question or stretch?
Is it going to work every time if you just take the ratio and multiply and subtract?
Okay, what ratio?
So if it took 12 grams of carbon
Okay.
to 16 grams of CH4,
Yep.
you just divide 12 by 16, you get 3/4. Multiply that by 4.
4.
Because you're 4 hydrogen, and then you get 36, and then 48 divided by 36 as well, or subtract by 36 as well.
I think so. I think what you did there was you used the law of definite proportions to define the components of each, and then you used the law of conservation of mass at the subtraction at the end to find what was left. So I think that would work, assuming I followed it correctly. But yeah, yeah. There are multiple ways to do it, so I think you're okay there in terms of that. I'm not 100% certain, but 97%. So looking at it now, let's try another one. Oh, yeah.
Make sure I got it right. So basically you did 48 divided by 16,
48 times 4.
okay, which is 12, right?
48 times 4 is going to be
100 times, yeah.
180 something. Or so.
192.
Okay, 192. Yeah, that makes more sense. 192, like, I can do that. 192, and then divide by 16. So whatever's here, multiplied by the top, then divided by the bottom. And then that will equal 12.
So you should always multiply the top to this side number, then divide by the bottom.
Mm-hmm. Yep. It's the same thing as saying 4 times 1/2. 4 times 1 is 1, divided by 2 is 2. But in your mind, you can also reason 4 halves ends up being 2. So mathematically, they're the same as you go through it. So it's always this times what's on top divided by what's on the bottom. Okay? So let's try another one once. And this time we'll look for carbon instead of hydrogen. So how many grams of carbon are needed for 20 grams of CH4? So this time, how many grams of carbon are needed for 20 grams of CH4 to form? One thing I should say as well, if in high school you learned about the idea of limiting reagents and so forth, we are not doing that in this course. Okay, so you can always assume you have whatever you need of whatever is not listed. So you don't have to worry about that ever.
Is that a different question?
Yeah, that's the next question, sorry. I was just thinking that, probably. Okay. Does everyone have their ideas for the CH4 question? 15? Is that what everyone's getting? 15? Not 15? Okay.
You got 5.
5. Okay, so let's walk through it and see where we stand. So 20 grams is given to us to start with. And it wants us to find grams of C. So then we need a relationship between the two. Well, lo and behold, we have one from over there. And looking at that, we're going to put grams CH4 on the bottom and grams carbon on the top. So what number am I going to put in front of my grams carbon?
12.
12. 12, because that is what our relationship says. And then that is going to form 16 grams of CH4. So grams CH4 are going to cancel. Grams carbon's left over. And then doing the math, 20 times 12 is 240. Divided by 16 is going to be 15 grams of carbon. 15 grams of carbon. You may not have been able to set that up all on your own, but are you able to follow along with the thought logic of it? Yeah.
Where did the 12 come from?
Okay. So over here in this relationship that we have, what we're saying is that 12 grams of carbon plus 4 grams of hydrogen equals 16 grams of CH4.
And is that just constant for
That-
these types of questions? And then-
Well, that's always going to be true, actually.
Okay.
If something like that is given to you, absolutely, it's constant forever. Later on in the course, you'll be coming up with the numbers themselves. It's not particularly hard. Like for example, 12 carbon. If you look to the periodic table, what number is under carbon? 12. So that's where it comes from. Hydrogen is 4 because hydrogen in the periodic table is 1 and you've got 4 of them. So you'll be able to do that. You're not expected to at this point, so you can just trust what's
So-
given to you.
So the 4 at the end of CH4 is because of the 4 in front of the G?
Opposite that. We're going to talk about it later on. We're going to spend like a week deriving it and stuff. But the 4 in front is because there's a 4 there.
Okay.
But don't worry about that at all now. Okay, it's going to be given to you such as this at this point.
I was just about to say that would be associated with that question, right?
Yes.
That you would have that.
Yes,
o-
this
written over there.
would be over there.
I
Yeah.
wasn't even looking over there. I was
Oh,
just looking
I'm
at that,
sorry.
and I was like, okay.
I'm sorry, I didn't. Okay. Yeah, I just didn't want to rewrite it. Oh. Again, I'm lazy, so call me out on it if you get confused. Other questions? Yeah.
Maybe I just wasn't paying attention, I don't know, but how did you get 15?
Okay, so when the numbers cancel out and you got grams C left over, then it's just a matter of doing the math. So 20 times 12 is some number, I forget what it is, 240 I think, divided by 16 is going to give you 15 then. Okay. And actually, that's a question. I'm glad you asked that because that trips up a lot of people. Like I'm up here on the board and I do and I don't think about it because I'm so used to it. But mathematically, it's 20 times 12 divided by 16 is the way that you go about doing it. And I'm always negligent in actually writing that out or something. Yeah.
So I always remember something called PEMDAS. It's PEMDAS.
Oh, the order?
Yeah, you always do parentheses.
I don't know what it means though. What is it?
It's like the order of going about algebra.
Okay.
Things. So you would take care of what's in parentheses first.
So
and
like
then
12 divided by 16?
Yeah.
Right.
Okay.
And then exponents, and then multiplication, then division, which is why we have 20 times 12 divided by 16. And then addition and subtraction. And
Okay.
that's
The other way you could do it, which probably fits better with what you're saying, is 12 divided by 16 is going to be 3/4, 0.75 times 20 would give you 15 as well. So I guess either way would be fine, yeah, absolutely. Just as long as you can remember what you're doing there, then you're good. I really don't want you guys to get tripped up in this class by math type things like that. So if you're having issues, let me know. That's not the point of it. You've got enough to worry about in terms of coming up with the relationships and so forth that I don't want the math to be the issue. Okay, moving on unless we got more questions. Okay, so I start writing out the next question for us. And we'll get rid of this relationship because we're going to need a new one. So, if 2 grams of hydrogen and 16 grams of oxygen form to make water, how many grams of oxygen are needed for 57 grams of water? So if 2 grams of hydrogen and 16 grams of oxygen form to make water, how many grams of oxygen are needed for 57 grams of water? Go ahead and get started on it. In a minute or minute and a half, 2 minutes, I will draw out the relationship for us to make sure we're all on the same page. And then I'll give you a little more time to work through the rest of the problem. Okay, to make sure we're all getting started, if we start with 2 grams of oxygen, 2 grams of hydrogen plus 16 grams of oxygen, that's going to form water. So how many grams of water are we going to form from 2 and 16? 18 grams. Because we have 2 grams going in there, 16 going in there, so we have to have 16 coming out. So now with that, let's go ahead and see if we can solve the problem. I'll give you 2-3 more minutes. Everyone got their ideas down? Okay. So looking at the problem, we're going to ask ourselves first, what is given to start with? And that's going to be your 57 grams of H2O. And then it's asking us to find grams oxygen. So we need a conversion between the two. And looking up there on the board on the other side, we know that for every 16 grams of oxygen, we're going to get 18 grams of H2O. Questions about that setup? Does everyone feel comfortable with getting to that point? Okay. Then we're going to cancel out our water. Oxygens match, so it's a matter of doing the math. So here we are, 57 times 16 is 912, divided by 18 is going to be 50.7. Yeah.
Ah!
50.6. I rounded it. Oh, wait. Yeah, 50.7. 51 would be fine, anything like that would be fine. Okay, so that would then be the answer. So if you started with 50.7 grams of oxygen plus the hydrogen you need, you would end up with 57 grams of water. Good? Yeah.
Would you say this is about a mid-level question as far as what the exam?
No, I would say this would be an upper level, especially starting from the beginning where you've got to derive the relationship and then use the relationship. That would be one of the upper level type questions. I would say, yeah, definitely. For the difficulty students have with it, and so, yeah, absolutely, upper level.
So you're always obviously gonna add the two together, so obviously the 2 and the 16, whatever the two elements are giving you. So that's
Mhm.
always gonna give you your starting point of your 18.
Well, unless for the fact that one of that's given to you is this part, and then you'd subtract, but yeah, you would add up your two components to find your third component there.
That's kind of your missing.
Yep, that's the first step, so that you can come up with this relationship. Because even if you did it the other way, and you wrote this down first, then you would get to this point empty, and you would say, okay, what's the relationship there? And then you would have to go back and come up with a relationship there. So you can either get the relationship first and use it, or set up your problem, realize you need the relationship, and then go back and get it. Either way. Okay, now, one that's not nearly as difficult would be, how much hydrogen would you need to form 57 grams of water? You can do it the same way. You could actually put your 2 grams of hydrogen here and 18 grams of water and calculate it out the same way. Or, what would be the other way you could do it?
Subtract 57 minus 50.7.
57 minus 50.7. And that would give you the amount of hydrogen you need there, because the law of conservation of mass. So it'd be 6.3 grams is the way that
Why
you
did
do
you
it.
do it like that?
So you know that in the end you're going to end up with 57 grams of water, and it takes 50.7 grams of oxygen there.
Oh, so, okay.
So you can take this minus that to find just your hydrogen component as
Okay.
well. Or, if you would prefer, you can put 2 grams hydrogen there, and then that, and then do the same thing with the 57, you'll end up with a 6.3. There it is. Okay. I think that's enough math for today. By far.
Do you have any extra, examples, problems for the conversions, like on Blackboard or something?
I don't know if I have any up there now. I have, in the old exams, there are some. And I'll also give you the keys to the old exams too, just so you've got those. But, you want me to write 5 of them?
Well, I just struggle with all the conversions,
Yeah.
whether it be from milliliters to liters or whatever, I struggle
Mhm.
with all of them.
Okay, so a couple things you can do. I'll remind you, you can go into the CK12 where the book comes from, and in the sections for the different conversions, then they have practice problems for it and so forth. You can go online and just type in metric conversions, and there'll literally be hundreds and hundreds of high school ones that usually have the keys with you. Or you can just shoot me an email, and I'll write some for you. It's not a big deal at all. Let's see. I may just steal from another book, but it's not a big deal. Okay. So just let me know what you need or what you want. Okay. Conversions. Some people in this class really like math. Some people really don't like math. So I try and balance the course as much as I can, and I end up with little math compared to the other stuff. But at the same time, chemistry does require some math, so that's why we spend time and we do it and so on. But I don't want the math to be the big issue. I know for the last half hour we've talked about math and so forth, and that's fine. But realize last class period, the class period before and so forth was basically no math, except for density and so on. The rest of today will be no math, unless you count simple subtraction. Okay. Last chance for questions for now, before I move on to lecture for the day. Okay, good. I'm glad we got through that, and hopefully you see that it makes sense to you as we're going through it. So last time in lecture, we were talking about the three different laws. The law of conservation of mass, the law of definite proportions, and the law of multiple proportions. And all of those laws talked about the behavior of atoms. So you had a certain atom and it acted a certain way. In elements, atoms are always the same. Atoms of different elements are different from one another. You know, atoms exist as the smallest unit of an element and so forth. So we talked about all those things. Now what we're going to do is we're going to skip forward in history about 100 years. A lot of that work was done around 1800. We're going to go forward to about 1900 now. And science has evolved in a lot of different ways. And one thing that's now available to us is electricity and batteries. And because electricity and batteries are available, we can start doing a lot of things we couldn't do before. And because of that, scientists were now able to figure out kind of the makeup of atoms. So the next section that we're going to talk about is going to look at 3 different experiments that scientists did to understand what makes up an atom, why atoms behave the way they do. And the first one is called the cathode ray experiment. This was done by Thomson in 1897. Now, what he did was he basically discovered cathodes, they're called. We know them by a different name now. But here's the setup of the experiment. You've got a glass tube that's under vacuum so air doesn't get in the way. You've got one piece of metal here and another piece of metal here. When you pass electricity through it, he could see that beams of something left the negative charge plate and went to the positive charge one. So little beams or particles of something left here and went over here. The tube was actually coated with something, and that's how you could see them as they were going through there. So they were zipping through there, and then once he put a magnetic field close to it, he saw that these particles bended towards the positive plate. So some sort of particle was leaving metal, and it was curving towards a positive plate. Now, he thought, well, that's interesting. What will happen if I change the metals? So he changed the metals, and he saw that the same particle was being ejected out of the metals. So he changed the metals again, and the same particle was. So he knew that it wasn't atoms being shot through this tube, because they would act differently from one another for each different element. It's got to be something else that's present in all different metals that's ejected out and then curved towards the positive thing here. He called them cathodes. Nowadays, we actually call them something different. So it's a particle that's present in all atoms, and it has a negative charge on it, so that it's directed towards the positive plate. What do we call the negative particle of atoms? Electrons. And this is actually the discovery of electrons. What he found was that as he passed electricity through the metal, electrons are ejected out of the metal, and then they move towards the positive. If you put a magnetic field here, they're actually curved towards the positive of that. It's the same thing as magnets when you're a kid. If you've got a plus magnet and a minus magnet, they're attracted towards one another. The same thing happens with charges. If you have a negative charge something and a positively charged, they're attracted towards one another. And this absolutely works this way. You can find YouTube videos showing you this. And they'll move the magnets and you'll see this light beam bend. I shouldn't say light beam. Beam of electrons bend and so forth coming out of it. So from this result was the discovery of electrons. And it was interesting for a variety of reasons. Largely due to the fact that all metals that he tried, all the different elements that he could try, all showed the same particle coming out of them. So he knew that it must be some underlying particle in it that was coming, and that was the electrons. He knew that they were negatively charged because of the way that they bended, and he had a rough idea of the mass. He couldn't separate the mass and the charge from one another, but he knew the ratio between the two of them from this experiment. And that actually comes from the mathematical modeling of the curve, which we're not going to go into at all. Okay. So the cathode ray experiment is actually the discovery of electrons. And once he discovered electrons, he tried to explain the atom as this. This picture here is called the plum pudding model. I've never had plum pudding. Anyone ever had? It's an English dessert or something. But what it means is that you've got some positive stuff that makes up the bulk of your atom, and then you've got little tiny bits of your negative electrons mixed into it. And this was the model that derived from the cathode ray experiment. It's actually very, very wrong, but it's one of the first models to try and explain what actually makes up atoms. As a side note to this experiment actually discovered X-rays as well. So when these particles are zipping down between the plates, if it zips down and then hits the metal plate here, there's a lot of energy from its motion that's stopping, and that energy has to go somewhere. So what happens is, as your electron zips down, when it hits this plate and stops, the energy goes off as X-rays. And then this led to the discovery of X-rays that we use quite a bit today. Questions about that? So all of these experiments are actually very simple. They're not advanced in any way, shape, or form by today's standards, but they were able to figure out some little part of the atom as we're going through it. Okay, so that's the first one. It's the cathode ray. Here's the second one. This one is the oil drop experiment. And this one's my favorite for a lot of different reasons. One of which is, right here, they call this an atomizer, but it's a perfume bottle. It's a fancy name for a perfume bottle at the time. So what is happening in this instance is you've got oil that's sitting in our perfume bottle, and then we spray it out. As the oil leaves the nozzle here, it rubs against the sides of it, and it picks up an electrical charge. This is the same thing as, I don't know, do any of you have little brothers and sisters? I have a little brother, and I used to torment him nonstop. When I was a kid, I used to, in my socks, rub my feet on the ground, and then put my finger up next to him. What happens? It shocks him, right? This is the same thing that happens here. Just like with our socks, when we rub it on the ground, we build up an electrical charge. As the oil droplets go through the nozzle, they pick up an electrical charge. And that electrical charge is electrons. I didn't say it in the previous slide, but electricity is just flowing electrons. That's all electricity is. That's why there are two prongs on the outlets, because one is taking electrons out of the wall and taking it to whatever is doing the power, the vacuum cleaner, the blender, whatever, and then the other one is returning electrons back in. So it's picking up this electrical charge and electrons. So there's some electrical charge on our little tiny oil drops here. They're falling into the bottom chamber, and this hole is supposed to be a lot smaller, but it's drawn bigger so you can see it. And they're falling down into here. Now, in the bottom chamber, we have an electrical field. So if I draw this on the board, here's the bottom chamber. And we have a positive charge at the top and a negative charge at the bottom. So these oil droplets come in, and they have a negative charge on them because they've got extra electrons. So as it sits here, what's going to happen in relationship to the positive? Is it going to be pulled towards the positive or pushed away from it? Pulled towards it. So you're going to have a charge effect pulling it upwards. And actually, you've got the same charge effect from the bottom, because two of the same charge don't like to go towards each other. Like if you try and push two north magnets together, they repel each other. the same thing occurs here. So you've got an electrical charge that's actually being pushed upwards by this electrical field, but at the same time that that's happening, you have gravity pulling it down. Now what's cool about this experiment is by changing the charges on these things by just a little dial, you dial the charge up or down or whatever, and when you hit the right value, this oil droplet is going to float right in the middle. And it will just sit there. So in that picture there, we have a microscope set up on the side, and you look in with the microscope and you watch the little oil droplet just float in midair there because of these charges associated with it. So it's sitting there floating, and what that means is that the electrical component is equal to the gravity component, okay? Because the force pushing it up and pulling it down are equal to one another, so it just sits there and floats. Well, gravity is very, very well understood. So because we know this side, we can figure out what this side is. And by doing this, we found out a couple things. We found out the charge of an electron and the mass of the electron. And you can figure this out mathematically. There's a variety of ways to do it. But in the end, the important thing is this experiment actually showed us the charge and mass of electrons separately from one another. And I like it because just imagine this little oil droplet floating in midair, just hanging out. Now, I guess questions about that? Yeah.
Well, it's not really a question, based on
Yeah.
like, so let's say like it's on an exam or whatever.
Mm-hmm.
Would you ask like how would it work or like what year was created? Like how would you answer a question based on that?
In the past, I've asked questions such as, what does the oil drop experiment tell us about the atom? So in that case, it would be the charge and the mass of the electron. I could also say, in more of a short answer type question, explain why the oil droplet would float in the oil drop experiment, something like that. That's really, I think, the only ones that I would, that type of thing. I wouldn't ask necessarily for the name of the person or the year or anything like that, so I wouldn't be concerned with that type of stuff. It's more just the general knowledge. The important thing about this really is the information that comes out of it. Okay. And what would that information be? So the charge of an electron, we're chemists, we like things simple. So we say the charge is -1. If you want to get into the metric system and so forth, there is an actual value associated with it. Physics class would probably make you memorize it and so forth. I don't do that. For a chemist, the charge of an electron is 1, and the mass is very, very small, so we say it's 0. Okay, so as far as a chemist is concerned, an electron's charge is -1, and the mass of an electron is 0. And that comes out of this experiment. Now, at the same time, similar experiments were done with protons. So if you imagine this is all done with this negative charge, you can do something similar with a positive charge going through it, especially the cathode ray experiment. So we also found, at nearly the same time, the second particle of an atom, and that's a proton. So the proton, so let's say type proton, electron, symbol, not very complex, P and E form, and then the mass, charge, location. So I guess we'll just do electron first. So electron, the mass of electron is 0, and the charge is a -1 in our chart here. The same time the proton experiments were going on, we found out that the mass of a proton is 1 AMU. AMU stands for atomic mass units. It's not really a metric thing, but I don't want you guys to remember the metric values for this. So we just say the mass of a proton is 1. And the charge was actually relatively close to the electrons, if not the same. It just had the opposite sign. So the charge of a proton is a +1. So from these experiments, we looked at the electron example ones. We were able to figure out the mass and charges of these two particles. The last particle in the set is a neutron. Neutrons took much longer to find because they don't have a charge. I guess I wrote that. So the charge is 0. So we couldn't play these same games with charges and electrical fields with neutrons because they don't have an actual charge associated with them. So the symbol for a neutron is N, and the mass is actually 1 as well. It's the same as a proton, as far as chemists are concerned. There is actually a subtle difference between the two in terms of masses, but for a chemist, we just say they're both 1, and we leave it at that.
Is this chart in the slides as well?
Yeah. It's also in the books, and you can find it just about there. There's our chart. Okay, so question, yeah.
Is only the photons measured in AMU?
Oh, no. It's called atomic mass unit. To be perfectly honest, it's kind of a made-up number to make the mass be 1. Like, it's really just a convenience thing. So it makes our life a lot easier though, so we don't mind. Okay, so finishing up the oil drop experiment. The oil drop experiment went and figured out the mass and charge of electrons, and the way that it did this was by balancing this electrical interaction with the force of gravity, which we understand. Electron has a charge of -1 and then a mass of 0 as we go through it. Okay. One more. You guys feel like you have one more to finish up in you? I'm seeing actually people shake their head yes. So, okay, great. This is the gold foil experiment. Now, it's still named the gold foil experiment because they used the gold foil to do the experiment with. The reason why they use gold foil is because you can make it very, 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 very thin. Anyone ever use gold foil to like cover something? Like you go to the Hobby Lobby or someplace and you buy gold foil, you can get super, super thin stuff here. So when we were talking about the atom, remember we thought that we had this smear of positive spread throughout, and then we had negatives throughout. So the positive is the protons, so you would have mass spread throughout the whole atom here. So if you think about this, if I shot another particle at it, if I shot some sort of particle at it, it's going to hit mass and then bounce off in some direction. And this is what this experiment was supposed to prove. We have here, it's called the alpha particles. Really, just think of it as something with mass. It's shooting down, and it should hit these atoms of gold and then bounce off in weird directions. Just like if you're shooting pool and two pool balls meet, they bounce off one another, right? That's the idea. But what we found instead is that when we shot these particles here, most of them went through. Okay? Most of them went completely through the gold foil without actually hitting anything. So if I had atoms, say you had another atom packed in here like this and so forth, how could they do that? So what they ended up doing was they had to change their overall idea of atoms and the shapes of them. So they believed that mass was evenly spread throughout. Well, from this experiment, they found out that that's not actually true. And instead of being spread throughout, the mass is contained in a small area. Generally, we say in the center of the atom. So that way, if this particle is shot at the atom, all of them that don't touch that center pass right through, but the ones that touch the center bounce off. And this explained exactly what we saw in the gold foil experiment. Most of, 99% of the particles shot at the gold foil went straight through. But then every once in a while, there was this rare one that would actually bounce off in some direction. This bit of mass in the center of the atom is called the nucleus, and it contains the protons and neutrons because they have the mass associated with it. Also from this, we were able to figure out that it's positively charged, but that shouldn't make much of a surprise to you, because if the center of the atom, the nucleus, has protons and neutrons are positively charged and neutrons are not, so the overall thing should be positively charged. There's nothing to cancel out that positive charge there. So that is the discovery of the nucleus, and I think that's where we'll end today, and we'll pick up there next time and talk a little bit more about the implications of it going into the next section. Questions? Okay, I will see everyone next time then. I guess Tuesday for class. Yeah. I'll make it the same. So I'll make probably one point for your name, 3, 3, 3. Okay. And then I'll scale that out. Okay. Oh. I forgot clippings. Go ahead. No. So for 112, the lecture and the lab are separate. You receive a grade for here and a grade for lab. Yes. That's okay. It's not a big deal at all. Yeah. Yeah. No. There's so much you see. Oh no. No, don't sweat that at all. The whole reason why I do it is so that I don't get into anything. I've never seen this situation. Right. So, yeah, no.
Yeah, I'll keep you posted on what's going on.
Yeah. Yeah, no, that shouldn't even, the score here doesn't, minimal effect. I appreciate it. Oh, no.
One question, it was really strange.
Yeah.
I was using my iPad to
Okay.
submit my clipping,
Yeah.
which I ended up having to do it for the regular desktop,
Okay.
but it pulls up this weird, I'm just gonna show it to you.
Okay, yeah.
I
By the way, I
didn't know-
forgot to talk about clippings. I failed on my list. We can talk about it next class.
If we, submitted through Blackboard, we were supposed to email our actual article to you, right?
You don't have to. It's kind of, if you want to, please feel free to do
'Cause I
so,
couldn't-
but you don't
I
have
didn't know how to put the article into the
to. You can
Blackboard.
just, like in
I'll
your
work
clipping
cited.
assignment, just at the bottom say article is this. And
I
that's
just put it
fine.
as a
Okay.
website.
Yeah.
I emailed it to you and I put it at the bottom.
That's
I'm
perfect.
works cited and I,
Yep,
so.
you went above and beyond.
Okay.
Great.
Okay. So weird. It goes like this. Yeah. And then swipe to open it. Okay, so I already submitted it, so what we do is after I swipe, and then it brings up this thing where it asks you to attach a picture. I was like, well, what is it to do? It was so weird. So I ended up just going to the desktop version and
Yeah, that is
being
weird.
like, okay. Not that it's a big deal, I just
Is
would like
that
one
the,
of
is that the Blackboard app that
Yeah,
you're using?
yeah.
I don't normally work with that, but
Yeah.
I know other people do, so I will look into it
Okay.
and then see what the deal is. I mean, you can always just do it that way, or you can email me or whatever, it's not a big deal,
Well,
but,
I ended up submitting it like through the desktop version, which is fine, but I just didn't know if you knew that it was.
no, I didn't, I'm glad you told me, so I can look into it, thanks. Yeah,
So if I, like, I get the whole concept of it now.
okay,
I know that, like, I would mess up, like, on a certain thing, like, for example, like, you did, like, this is how I thought how you got the 4, because even though the 4 wasn't listed on the actual problem,
Mhm.
I thought you got the 4 when y'all subtracted the 12.
that's exactly how I got it before.
Yeah, and then I thought you'll do the same thing on this one, but y'all got it.
Okay, so the difference on this one was the fact that 2 and 16 add to form H2O, where in the previous question, I should show you so much clearer. It says it takes 12 to make 16. So this is the product here. So this is like afterwards, where in the previous, in the other one, I gave you the 2 before.
Okay.
So that was the reason why there was a difference.
And if I need some more columns, I'll just email you.
Yeah, no, that's, yeah, not a problem. Since several people have asked, I'll write like 5 of those and put them up on Blackboard today too.
Thank you.
Yeah, no problem. Let me know if you're having issues, Doc.